Welcome everybody to our webinar that we're holding during World Space Week. And the theme for this year's World Space Week is living in space. So we're joined by Bjarke Gotfredsen, my co-founder in MaxIQ Space, and he's going to be sharing with us his views on living on Mars, 3D printing, and robotics at work. Bjarke did a fantastic presentation on a similar theme some time back, not too long ago, for the Department of Education across the US. Every year when they hold challenges regarding space and STEM education, we are one of the main participants. So Bjarke has a background very firmly in software engineering. However, even though he hasn't got any formal training in designing and building electronics, he has managed to, over the last 10 years, design and develop and build and produce all of our X chips that we use in our programs. And we are currently bringing out our third version of those X chips. So Bjarke, what I'd like to do is that I'd like to hand over to you, and I will stop sharing so that you can begin your presentation for us.
So my name is Bjarke Gotfredsen, and I am the co-founder, as Judy mentioned, together with Judy, and I'm kind of like the person responsible for, let's call it all the technical stuff. So that's the hardware, the software, the server side, and we've been focusing on space and technologies to go into space one way or the other, especially so high school students can use it, that have ended with that both university students and PhD students are using it in upper classes and into primary classes. We have grade 4s using the UK, and we even seen younger classes uses our technology. So we're very happy about that. And one of the reasons why we also did it was that we thought there was a future for this technology, which I will come into in this thing here, this presentation about living in space. So let's start. I'm going to talk mainly about, in the beginning here, human versus robot. There's a big reason why we use robots, and when we want to live outside our planet, that becomes much more important. Very short about the history, and then what is a robot? Everybody have an idea about what a robot is, but what does it really mean? And then what will it take for us to build something on another planet, such as Mars? So the Mars rover is a robot we sent to Mars, and that lasted from 2004 to 2018. It was only planned to last 3 months, but it lasted 14 years. And eventually it gave up because its solar panel got covered by dust from a dust storm, and without solar panel running, it couldn't generate electricity, and therefore it couldn't drive. So it died there. And as everybody hopefully know, Mars is a planet where there's nobody else, so nobody could go there and dust off the solar panels, so we could get it running again. So that's robots. That's an example of a robot. So what I want to talk about here is kind of like put a robot on the one side of the swing. What do it's called, this thing here? And we put
it's called a seesaw.
That's the word I was looking for. We have robot on the one side of the seesaw, and we have a human on the other side of the seesaw. Because they require different things, and they are vulnerable in a different ways. So what we're going to look at is all these different factors. The air is, we need air to breathe. So air, the temperature. Right now it's nice if we can go outside, and it's maybe anywhere from 15, 25 degrees, sometimes warmer, sometimes colder. But it's not that cold and it's not that hot. Water, and food is what we need. Radiation is what we don't need, so we need to be protected from that. Weather is great. It helps us with a lot of stuff, but sometimes weather can also be bad. Light is important. Gravity plays a big factor, and so does pressure. We live in a world where there is a air pressure around us, and that's important for our body to work properly. Regolith is like the soil on a planet. We call it soil here. On a moon and Mars, we call it regolith. Then there's an atmosphere. That's the thing that holds the air to the planet. And finally, we have a function called electricity. So if we take, for example, Earth, we have all that. The weather we kind of like can complain about, so therefore I give it like a little cross there, because there is actually celestial bodies where there's no weather, and then it's much easier. When we build something on Earth here, we have to make sure that it can take a storm or earthquake or flooding and that kind of stuff. So therefore, weather is not like the best thing. We need it for all kind of other things. So it's super important we have it. But when it comes to building and things like that, then it could be nice that if there was no storms or flooding or anything. So there is this rule of 3. And we just have to have that in mind when we kind of like consider where we want to live. And that rule of 3 doesn't count for robots. This is for humans. So we can live 3 minutes without air, 3 hours without shelter. And shelter just means like that we can keep ourselves warm. So we don't freeze. So that can be a spacesuit or, just normal weatherproof clothes. We can last 3 days without water and 3 weeks without food. So that is some of those things that's important for a human. Robot doesn't need air, shelter, water, and food. It needs other stuff, but none of these things here. So, can you hear this, Judy?
No, we can't hear him. We can't hear his voice.
Okay, so this is from the Martian. So I have a few clips here from a couple of different space movies, and unfortunately you can't hear him. But what he's talking about here is that he just realized that he's alone on Mars, and the rest of the crew have left him. So he is nervous about that the oxygen generator, it doesn't work. He's nervous about the water recirculation system is not working, and if he can get through all the different things, he's probably going to die of hunger because they were not meant to be there that long. Great movie. I really suggest if you're interested in space, this is one of them you definitely have to watch here. So if we go to Mars, and this movie we just saw here, of course, about the Martian, and take that as our first example, you can see here that there's no air, there's no breathable air for people. The temperature is very radical, so we can't live without being in a spacesuit. We have to have a spacesuit anyhow for air, but now we also have to have a spacesuit that kind of like can keep us warm and cold at the right time. And then I have this, let's call it question mark here about water, because we believe there's water, but I like to see it. There's definitely no food. And radiation, there's plenty of. We are protected here on Earth by something called the Van Allen belt, but on Mars they don't have that. They don't have iron core, so there's rotating, so they can't create a magnetic field that can protect against radiation. So there's radiation problems on Mars. There's weather. In this movie we just saw, and I'm gonna show you a short clip here, they actually have to leave because of the weather. There is light, however, because there is an atmosphere, and that atmosphere spread the light that comes from the sun. So you get the light all around on the planet, similar to on Earth here, even though the intensity is not the same. The gravity is much lower than here on Earth. So if we stay too long on Mars, we will have a problem getting back to Earth. It's easier to get to Mars because it's lower, so we just feel much stronger. But once we are kind of like used to that and then want to go back to Earth, it's going to be much tougher for us because we just feel everything is so much heavy and we don't have the muscles to that. And it takes time to build that up. There's soil on Mars that's okay. And the reason why it's okay on Mars and Earth is because we have a weather, then the soil on Mars is kind of like polished. What I mean by that is that if you take, for example, on a beach and find a broken glass, if it's been lying there for a while, it's not sharp anymore. The sand and the weather have kind of like polished the edges of the glass. But if a newly broken glass, it's very sharp. On Mars, because they have the weather, the soil has kind of like been polished off. And there's an atmosphere, as I mentioned. It's not necessarily the atmosphere we can use to breathe on, but there is an atmosphere. And of course, we can put solar panel up, so we can also do electricity. And we can also put a nuclear reactor up, so we can do electricity that way. But we can't do any kind of combustion, so like coal-fired power station or that kind of stuff, because that needs oxygen to operate. And there's very little oxygen on Mars, not enough that we can do that kind of stuff. So this thing here is the storm that's coming in. So just to show the weather that kind of like demonstrated here on Mars. So that's the reason why the soil is okay, but there is also weather here. And of course, in this sequence of the movie, that's very early in the movie, they have to take off because of this storm here. If you then look at, oh yeah, and then I just want to say this is from another movie where there is a kid who's born on Mars, and in order to actually get back to Earth, they have to operate all his bone structure because the bones are not strong enough to hold him on Earth because they were meant for the gravity on Mars. And that's actually a realistic picture. If we go to Mars and start procreating on Mars then and want to go back to Earth, we're going to have a problem. And the same problem as if we today want to go to say Saturn or Jupiter or any of these bigger planets, we can't. We're simply not strong enough to survive standing on one of these planets. We're getting crushed by the weight of ourselves on planets like that. So the other thing is that this is also an example from the Martian here, where the door blew off, if I can use that simple term here, and he's now trying to cover that hole with some plastic seating. And of course, I will be very nervous on going to Mars if the hectic temperature swings and storms and different in pressure was separated by a Ziploc bag, and that's big size there. So have that in mind when we talk about the resting here. So the next one up is the moon. And if you look at this thing here, you can see the first number of things. There's no air, the temperature is very hot and cold. We believe there's water, but let's see it first. There's definitely no food, plenty of radiation, but there's no weather because there's no atmosphere, and without atmosphere, there's no weather. And that means that whatever we build and construct there, it doesn't, if we can get it to stand there, it will stand there until somebody comes and puts it over. And that's not going to be the weather. So that's going to be some man-made stuff. So we are able to construct things on the moon without being nervous about how to survive. The light, because we don't have an atmosphere, the light doesn't get spread on the moon. So we just have this lonely light bulb in the sky, which is the sun. And therefore it looks much different on the moon, that there's just a light from one direction. If you stand behind, if you stand in a crater or behind your rocket ship you landed on or whatever, it's completely pitch black all the time. And of course, another very important thing is that while we have a 24-hour day on Earth, on Mars we have like around the same length. It's like slightly longer. But on the moon, the day is, I can see I froze here. On the moon, the day is actually 2 weeks long, and the night is 2 weeks long. And when it's night, I mean, it's just black. So electricity is a little bit more difficult because we have to have the solar panel to operate for a much longer time. So, sorry, I just want to check here. Yes. The gravity is the same problem as Mars. It's just even lower, so it's even bigger problem. The pressure, there's no atmosphere, so there's even lower pressure on the moon. So it's even worse. That means that if we have to have a place we live in, we have a much bigger pressure difference to the outside, which just makes the construction that much more critical. The regolith, because there's been no atmosphere, it's like newly broken glass all over the moon. There's very fine, but it sticks to all the clothing. It's very sharp, and it's very what they call corrosive glass that just cuts. So all the sand, all the dirt on the moon, the regolith is just like very small piece of a glass. And of course, there's no atmosphere. So on Mars, we can use the atmosphere for different things. We can't breathe with it, but they have CO2, so we can actually extract different things from the atmosphere on Mars. Here, there's no atmosphere. And again, we can do electricity. We can put solar panel up. We can put a nuclear reactor up, similar to on Mars. This is another movie, and I think this is the last clip I'm showing. This is Gravity. And I like this little sequence here where they try to catch like the knot. This is like Little Ella on the moon also. It's very interesting to see when the Americans landed on the moon back when I was a little boy. You know, they jumped around because they could, but you know, after a while, it started getting annoying when you're used to gravity and used to the effects on Earth. It's getting much more difficult to handle when you go to another planet. And this is like one of the first, actually, I think it was the first space flight where SpaceX sent people to the International Space Station. If we take an asteroid, it's the same as a moon. It's just much smaller, but otherwise it's the same. There is no weather. You can probably put a reactor up if it's big enough, a solar panel up. We don't know because there's so many asteroids. We don't know what the day and night is going to be like. We've identified the asteroid. We can, of course, identify that eventually. There might be water, depends on what asteroid we find. But in reality, asteroids is, it would be much easier to go to the moon, land on the moon, live on the moon, than any asteroid which is much further away. And of course, on a spacecraft, we don't have water. I mean, we bring water, but it's not like we can find water on a spacecraft. It's like there, if we brought it, similar to on all the other places where we might not find water. But hey, there's no weather. And yeah, we have electricity, like on the International Space Station. There's no weather. There's electricity from the solar panels, but the rest, it's not great. And all that I mentioned because you can see the needs here. Only the last line is where robots are fine. A robot doesn't need air, temperature, water, food. They don't mind radiation, weather, light, gravity, pressure, regolith, atmosphere, all that. That they don't need, but they need electricity. On the other hand, we've lived on this planet here for millions of years without electricity, so you know we could survive without it. But when we have to go to another planet, we just have to consider that we are built as a human to live on this planet. Over millions of years, we developed so this planet and us works together. We breathe oxygen because there's oxygen on this planet. It's a highly flammable gas that we're breathing. And if we ever find aliens and they come from another planet, they might breathe something else that's on their planet. So our life form here is determined about how this planet was. And the other planets not like that. Maybe they have been 3.5 billion years ago, but they ain't anymore. So that's the scary thoughts about human versus robots here. So we have actually we went to the moon back in 1968. We first flew around the moon. We didn't land on the moon, but that was the first time the human went outside what's called low Earth orbit. So low Earth orbit is where the International Space Station is. It's like 400 kilometers up, and at 400 kilometers we are below the Van Allen belt. And Van Allen belt is what protects us from radiation. So once we get outside the Van Allen belt, outside Leo, it starts getting much more difficult. So first time we did it was in 1968, and last time we did it was 1972. We haven't been outside Van Allen belt since. We have flown a little bit different, like with some of SpaceX's other missions. They're flying over the pole and things like that, but we haven't actually left Leo. And the next time we're going to do it, and I'm going to put a big question mark there, is Artemis 2. When I updated this presentation here, as Julie mentioned, I did a couple of years ago, we were going to have Artemis 3 in 2025. And we're still considering Artemis 2 in 2026, which I should probably put more than one question mark behind that. A little bit of stats here. The moon is, as I say, well, the low Earth orbit is 400 kilometers away, and that's like a 10 times around of Earth. The 10, it's like 10 times around. The distance to the moon is around 400,000 kilometers. The Bennu, that was one of the asteroid we visited, is 6.2 billion kilometers away, and Voyager 1, who has left our solar system and was sent up 50 years ago in 1972, I think it was, or 71, 72. And in a straight line, because it doesn't fly a straight line, because it has to get pick up speed by doing sling maneuvers around our different planets in our solar system. But by now, it's around 25 billion kilometers away. So far away. So that's kind of like what we have been able to send away. And the first human being have been away is, as I said, 400,000 kilometers to the moon for like a week at a time. So now moon is like one of the things that a lot of countries are focusing on, including the US and China, Israel, India, Russia, and so on. And that's of course because you can go to the moon in like less than a week, and you can be there a little and come back again. And it's like, it's such a short trip. So radiation, it's something you can handle on such a short trip, and coming back, yes, you still been in space for a long time, for a week, but there's people been on the International Space Station much longer, and they have been able to come back and survive that. Going to Mars is probably like minimum 4 years to be there, which nobody have actually done in space before. So when I first did this presentation, that was kind of like where we were. So you can see the United States, and then it said Soviet Union, but further down the list, it's also say Russia. And Soviet Union, of course, stopped being Soviet Union last century, and they're now Russia. So a number of these different countries have tried different things. So we talk about the moon here. Have you done a flyby? Have you done an orbit? Have you impacted on the moon? That means landed hard. Do we have a lander that has survived? Have you been able to put a rover on the moon? Have you been able to return from the moon? And we be able to have people on the moon? So only United States have been able to have people on the moon, but landing on the moon and sending stuff back from the moon with robotic United States, Soviet Union, China have. But this was like a couple of years ago. I kind of like have updated it to this new sheet here. And it's just to show, first of all, that some of the stuff that's new is like Japan have put a rover on the moon in 2024. And you can see that Pakistan had an orbit around the moon in 2024, and Mexico tried to put a rover on the moon in 2024. When I say try, it's because the red one was the mission, and red means it didn't succeed. So there's a continuous attempt to do the different things. But you can see the US, while they have been landing on the moon, they haven't really done anything since 1969. While China have their entire list is from the last from this century here, started in 2007, and then they have done stuff ever since. The same with India. So a lot of these countries are working on new stuff they've been doing here in this century here. Of course, Artemis is the program the Americans have to go back to the moon. And now there's a big conversation, especially in the US, because we have a new space race. The reason why the American was able to do it in the 60s was because there was a space race with the Soviet Union. So they spent all the money they could scrape together for this thing here. Now there's a new space race. China's probably going to win this space race, but that's the reason why everybody is like happy to now try to do something about getting back to the moon again. So in this thing here, I just want to talk a little bit about first of all a little bit of robot versus machine, because if we have to send robot, we have to kind of like figure out how ready are we with robot and what can we send, and then also like how can we get robot to work, because when I started working with robots many years ago, I have to program the arms movements all the time. I couldn't just tell it, go and grab something. Those things have changed now. So we have to see how difficult it is and how much can we ask a robot to do something by itself. Because if we have to control it from Earth every time it moves an arm, it takes at least 15 minutes for a mover arm command to go to Mars before it moves it. And then we have to figure out if it actually moved the arm, another 15 minutes. And then when we have to tell it again to move the other arm, you can see this is not going to happen anytime soon. So we have to say, no, go and, weld that pipe, and then it have to be able to figure out that itself. So let's look a little bit about a robot. And I'm just taking a simple example here, and I'm using this Roomba vacuum cleaner here, because that's a good example of where we have gone. So if I start with the first picture up here, when this robot, they came around, they just took a path. They went zigzag over the floor, and hopefully they caught the whole thing, and next night it will go around again and go around. Then we got into that they start being able to figure out there was an obstruction. Somebody had left their slippers. So we have to go around and not go into them or give up because there were slippers there. And then eventually we got into a situation where they drive around the first number of nights and map out the whole thing so they know what's an optimal path to vacuum clean the whole house here. So these days they can do much more. They can actually auto dock, and they can empty themselves in an auto dock, and they can recharge and all that kind of stuff. And some of them, like the one in the lower right corner, can actually also wash the floor. So therefore, it will have water, fresh water, and soap water and things like that, and will be able to dump the other one. So obviously, you still have to manually go and empty and fill up these things, but hey, you don't have to mop the floor. So the next step up from that is that now it can also recognize different things. Before, it just knew there was an obstruction in front of it. Now it knows it's slippers, it's your charging cable, it's a piece of fabric, whatever it is. So it kind of like can identify it, and that might be that some of these robots can actually pick up stuff and move it and things like that. So it has to identify it first, and it can figure out how it can pick it up, if it can be tolerated to pick up and all that kind of stuff. If it's actually, it's a paper ball that landed that should just be picked up and moved away. And eventually they do full mapping in 3D, and can of course do more and more that way. So the other example I have here is from Tesla. So this was Tesla full self-driving screen when it came out. I think this is a picture from 2025, so it's not a very long time ago, 5 years ago. It looked like that. Of course, they could the Tesla itself, they could put a nice picture of that, but all the other cars was like boxes and line curbs and line markings. It could kind of like give an idea about how it was, and put some dots where the white lines was, and curbs on some red dots and so on. And it could identify maybe some traffic lights, and then kind of like put them in the area where I believe the traffic lights are. And this is how it looks today. So now it can fully recognize the lanes and the cars. I mean, all this it does by cameras that they have, I think 8 cameras around the car, and it can see the different cars. And of course, the way that we drive is that we drive by also remembering that behind that truck there was another car that passed. So it will remember there are different things. It knows it doesn't just disappear. So when it sees some stuff, it kind of like sees some of the car, and it can draw the rest of the car because it knows how it's going to look like, all that kind of stuff. Sees the human, all other things. And the most interesting thing is like there's a website where the community actually logs in and tell how they're when they drive, they can upload the data from the car about how they drive. And probably the most important one here is that critical D stands for disengagement. So that means that the car stops driving by itself. It beeps and say, no, you have to take over. And right now, and when it just disengages, like you can see in the yellow one next to it, there's 32 miles. That's when people stop themselves. But if you want to know how the robot drives, then it's when that decides to stop. And now, if you drive outside the cities on the highways, you can drive 750 kilometers before the car disengages. And in the cities, you can drive 370 kilometers fully automated. You don't have to touch anything. So it gives an idea about how far we've gone. Obviously, if you take the steering wheel away, then it doesn't really help that it stops after 230 kilometers because, hey, what are you going to do? Get a new car. So, we have to get these numbers even better, but it's a good thinking that you can imagine you can drive 750 kilometers, which, most of us will be tired if we drove that long ourselves, but we could sit in a car and let it drive 750 and hope there's a garage when it decides it doesn't want to drive any longer. So that was a little bit on the robot side, and with the full self-driving, we also get into like how we program these robots. So we have the classical programming, and that is that we have rules. So, and then we have data. So we say rules is that you give me data 1, I give you rated data 2, and the rules is that you have to add them together. So 2 plus 2, and then the answer is 4. And that we can all understand. That's how we've been programming for a very long time. Machine learning, we moved it a little bit around. We still given the data, so we gave it 2 and 2, and then we gave the answer 4. And we say, how could you get to 4? And it comes out and say, well, the rule I'm making is that you multiply them. 2 by 2 is 4. And we give it another data, and then we say 3 and 3 and 6. And it comes out and say, well, I thought it was going to be 9, but if you say 6, I have to change my rule. So what if we say plus, we go back and figure out 2 plus 2, yeah, that's also 4, and 3 and 3 is 6, yes. So new rules is plus. So what you do with machine learning is you give it a lot of data, you give it a lot of pictures of a cat, a lot of pictures of a dog, and you tell them with all these pictures, this is a cat, this is a dog. Eventually, when it sees a completely unrelated picture, it has figured out what it is from these different pictures. That's machine learning, and that's in essence what AI is in a basic version. And when Tesla first started with that FSD, they had people sitting and analyzing all the video from these cameras and say, no, this is a car, this is a bicycle, this is a traffic light, this is street sign, this is a dog, and so on. And then kind of like 1-2 years ago, they went into using full machine learning, and it asked the computer itself to identify it, which I could do because they had now so much data where they have actually already told it what the different things were, and now it actually drives 100% without input from people. It knows all the different things it sees in nature and know how to deal with it. Here's another example here. So with traditional programming, you want to cook a chicken, you have your ingredients, and then you have the rules. You cut the vegetables, season chicken, etc., and then you make that. If you want to do machine learning, you say, listen, my input is a chicken and vegetable, and my output should be this thing here. You figure out how to do that. And just for the fun of it, I did that with ChatGPT here. So I wrote this thing here. I have a fresh whole chicken, a mixed bag of fresh vegetable, etc. Give me a short 5-point recipe with just instructions. And it didn't have to think long to actually give me a concise 5-step method for a rustic roasted chicken with vegetables. So great. And just so, I actually use ChatGPT a lot to figure out how to cook and do different things instead of actually going to traditional recipes, because I might not have what the recipe have. I might have other stuff, and I ask it to come up with some stuff. Over the time, it actually know what kitchen equipment I have, so it can go in and say, listen, I suggest you use this thing here, because in ChatGPT you can give it not only this, but you can also give it like the backstory of you. What kind of car do you have? What kind of kitchen equipment do you have? What kind of programming stuff do you do? And so on and so on. So here is a Tesla Optimus Prime. So this is the robot they start building. And this is, of course, also built because going to Mars, they have to have robots. So this was Tesla Optimus Prime back in 2023. It was able to move these blocks around. And yeah, some of this stuff we impressed of back in 2023. Nowadays, we require a little bit more. So the newest is that now it learned to do Kung Fu. So here it actually trains Kung Fu. And the important part in this training here is that it have to analyze its opponent and see where he hit and prevent the hit coming in. It have to keep the balance, and it have to actually use the rules from the Kung Fu to have this fight here. Now, I don't think that we're gonna do robots so we can do Kung Fu, but one of the reasons why they do it here is because they need to make sure that this robot can stand and anticipate and figure out how it makes sure it doesn't fall over, and when things are out of place, it can handle it, because that's how we as humans can figure out. And the reason why we do robot that looks human is because the world we live in is built for humans. The door handle sits in the height of the door, so most humans can grab a door handle. If it was a robot was all looking like vacuum cleaners, like I showed before, then the door handle would probably sit down at the foot, but that would be annoying for us humans. So everything we have is based on our hands. We have to use these hands to grab and hold on to stuff. And we have to have that coordination. We have 2 eyes so we can see depth and so on. So therefore, lot have decided, like, if you have to have a generic robot, if you make it so it looks like a human, not looks like, but acts like one, and have the same size and things like that, it's much easier to replace it. In the future, if you don't have a test of a self-driving, you might just get a robot and ask him to get into the car and drive for you. If you can drive, why shouldn't, you know, a robot be able to drive with the same kind of inputs? So now the next section is that we have to have the building blocks and we have to get them there. We have, of course, this issue with Mars being not around the corner. So of course, if we prefab something here on Earth, let's say a container that we can live in or whatever, then we have to send it to Mars. And Mars is flying around the sun like we are, but not in the same kind of like speed. So therefore, we have to, every 2 years, we can be aligned with Mars, then minimize the time it takes to send something to Mars. So 115 days is 3.5 months. So it's 3.5 months or double as long, depending on how lucky we are sending something to Mars. If we send software to Mars, well, it takes, again, depending on how far Mars is away, 15 to 25 minutes. You send a file there, over the air, it goes with the speed of light, so much faster than we can do as a rocket. And of course, if you print hardware on Mars, well, it takes a few hours to print it. So instead of doing prefab, we should rather send 3D printers to Mars and make them doing it there. And then when we kind of like design stuff, well, we don't have to design, you know, the housing and building and everything. We just have to make sure we have a 3D printer that is generic enough that it can do what we want it to do on Mars. And then we can always develop the software afterwards. So SpaceX are right now the only one who really focusing on getting to Mars. So there's no nation that kind of like looking at that. China is focused on the moon, the US government is focused on the moon and so on. But Elon Musk and Starlink is as a Starship, they want to go to Mars. And they have this audacious goal about sending 1 million people to Mars. But let's see when that's going to happen. It's not going to be a problem finding 1 million people who want to go to Mars. There's plenty people who, if you think back, you know, 1,000 years ago when people lived in Europe and they want to go to the US and they didn't know if they ever came back. There's plenty of people who want to be pioneers. But hey, if you have to go to Mars, you at least have to get onto 1,000 starships that have to be built, launch and fly and able to survive and things like that. So SpaceX is the ideal company to do that. You can see on the graph here that last year they had 133 successful launches and that's 10 times more than they had in 5 years ago. So they're running quickly uphill with all their abilities. So when Starship is ready, yeah, there's a good chance that that graph just grows. Now, China is also sending a lot of rockets up, but SpaceX still sends more kilo into space. So if you kind of like consider in weight how much they've been sending into space, SpaceX will sending more into space than all other space companies from any other countries in total, just because they are that successful with the Falcon and now a Starship. So the building blocks that we have to have on a planet, we tested a lot of these for a long time. So remember the first thing we talked about to survive was we can't survive more than 3 minutes without air. So let's talk about air first. So we have this thing here we call MOXIE, Mars Oxygen In-Situ Resource Utilization Experiment. Okay, so it takes the oxygen out of the Mars atmosphere. So remember that CO2 and the atmosphere is very thin. So when the dust storm blows there, it doesn't blow a rocket over like we saw in the Martian, because it's not a very high pressure environment on Mars. So you can see there the oxygen is 0.13% on Mars, versus on Earth is 21%. So we have to start a little bit before the human being comes to kind of like start taking that oxygen out. So you can see a small crew will need 25 to 30 tons of oxygen. So that's like a big tractor trailer. You see those that drives around with the big tube on the back. So we need that kind of oxygen, and it'll be much better if we can, instead of fly it there, then generate on Mars. And we also need oxygen to power our rockets. And we land there, it would be nice there's kind of fuel there so we can fly something back if somebody regrets the McDonald's on Mars. A MOXIE here requires 25 to 30 kilowatt of power, so we need power, either again solar panels or nuclear reactors. The next one is this WAVA, water vapor absorption reactor. So what that does is that it actually takes the water out of the Martian atmosphere. I have a Lake Tahoe here. I actually wanted to change that lake here, but the amount of water we need, of course, for human is it's more dense than air, and we just drink it from time to time. And again, we have to generate water if we put 1 million people on Mars. There is water on Mars, but there is probably not enough to sustain a big population, especially because we don't just use water for humans, we also use it, like I said, for rockets, and for if we want to grow food on Mars, then that's also water-based. So we need water for a lot of different things. Then the idea is that we can 3D print on Mars. The one thing is 3D print houses, so that will be a 3D printer like this thing here. So again, we are now testing all kind of 3D printers to build a habitat. And then the idea is drop one off on Mars, and then, here's two that is coordinating, building, kind of like, I wouldn't call it a village, but like a station to start from. And the whole idea is that they're going to use the regolith on Mars. They're going to use the soil there. They might need a few other things that we're going to, a binding material like cement or whatever that we send there. But the whole thing is that we have to figure out how we can build it on Mars. And therefore, if we have to generate, let's say, water out of the atmosphere before we can start doing that, well, then we have to have the WAVA first, etc., etc. So we have to send all that off. And we now are in the process of figuring out how we can do this thing. Obviously, there is also an alternative to build on top of Mars, and that dig a hole and get under the soil of Mars and live in caves, like we did here on Earth millions of years ago. But in reality, we like that if it could be on the surface of Mars, otherwise, why going there? And that leads me back to Tesla here. So Tesla is doing a lot of different things for SpaceX. That's kind of like mainly the same owner, Elon Musk. So they're doing solar panels and they do batteries, because that's one way of generate electricity and store electricity. They've done cars, like this is the Cybertruck. They actually done versions that is watertight, and because they're watertight, they're also airtight. So that means that the atmosphere you have inside the air you have inside the Tesla means that you can drive around the Mars without have to be nervous that you can't breathe. Obviously, there's no reason to roll down the window, because then it definitely, in a situation, you can't breathe. And also, because it's an electric car and not a combustion car, it can drive on Mars because it doesn't need air from the outside to burn fuel. which we use to here on Earth. And then, of course, the last one is that Elon also have a boring company where he bores tunnel. Right now, he's been building a tunnel from Las Vegas to underneath Las Vegas, so you can drive there. And his philosophy on Earth is that we build buildings that's it's like skyscrapers where we live like in 3D. We live in houses, we live in skyscrapers, but we always drive in one level, and that's the reason why we have the congestion. What if we could build tunnel underground and then drive in tunnels zigzag? Then we could overcome congestion. But all of the stuff he also have a little secret idea about how he can use that on Mars. So sending a Boeing machine to Mars to that dig underground tunnels and caves and things like that, so people can live there, is maybe also an opportunity. So in summary, we have to, and here's the blueprint of this thing here. It's going to be a little bit faster going. So we send the cargo there and we build our main hub, and we have communication satellites and we have a rover, and we get more cargo sent there. And then we, of course, have the MOXIE that does the oxygen and WAVA for the water. And then, of course, we have to have electricity for that. So either we have solar panels or we have a reactor, a nuclear reactor. And then we get the MOXIE and the WAVAs, and we can then power with these two things. We get a workshop, we get the 3D printers. And then when we have all that, we can consider actually to land on the moon and then start, on Mars and start living there. So that's kind of like the order. If people going to Mars, they're probably going to come back again, because there's going to be very little until we got all this other stuff in place. And while we're talking about the 3D printers, that is kind of like a thing we can send to Mars up front without knowing what we are actually going to build there. We can send drawings and all that kind of stuff. But what about electronics? And that's a reason why we kind of like also thought, well, what if we could send these different modules to Mars? We don't know yet how they're going to be done, but we don't have to do electronics factory on Mars. We can simply just do these devices and send them to Mars, and the robot can put them together and say, oh, by the way, we need an electronic circuit that can do this and a circuit that can do that. So for us, this is what 3D printing is for mechanics. This is what we are to electronics. And that, I think, is it for me. Thank you very much.
Great. Bjarke, thank you very much. That was absolutely wonderful. Do we have any questions? I'm going to have a look at the chat. Leanne, Monet, do you have any questions?
I don't have any questions, Judy, but I think this would be such an amazing presentation or to do a masterclass with learners. You know, this,
Yeah.
I mean, I'm already thinking of some of our grades where this would be such a wonderful introduction. And I think, Bjarke, you could even take it a bit further and then sort of then explain to them what each of the little chips are, you know, so that it's like almost an introduction to them using it in the classroom. But
Yeah.
with a project, like I mean, this is, I loved it. Thank you.
Thank you very much.
Yeah, and Leanne, yes, that's actually a really good idea, because if you have a look at if you have a look at the MOXIE and the WAVA, the thing is that what you want to know is you want to know your carbon dioxide concentration before you start extracting it, to extract the oxygen from the carbon dioxide. You'll also want to know what is the relative humidity before we can extract the moisture from the air. So yeah, there's actually a really nice link to the sensors that the students have every day, and then how they could use that. Yeah.
You're sparking their curiosity, because a lot of what you were saying now, you know, we've discussed it and we've looked at it, but you know, you're talking about things that are relevant that are happening on Earth, like with Tesla and what they are doing, and you know, just even looking at who's sending what up into space. Those are all relevant, um, but we do need to do those experiments on Earth before we can take them up to Mars or to the moon or wherever we're going to do it. We need to test it here on Earth.
Yeah.
And it's such a wonderful link for the children to connect what we do here and why it's important for in space. I see there is a question there, Judy.
Bjarke, are you able to see that question? Would the size of Mars be enough for human population?
Yes. Yeah. So the idea is, you know, so the people who dreams about us going to Mars is, let's just isolate it to Elon Musk. There's a lot of people who want to go to Mars, but they want to go to Mars the similar way that you know, our early explorer in Europe want to go to the US, or actually to India the other way around, and they spotted the US, and eventually people want to go there and live there, and that is of course of interest. And then the more and more move there, then at a certain point is maybe not interesting enough. So first of all, Mars is of course smaller than Earth, okay, but 70% of Earth is also water. So we can't live on the 70% here. So I don't know the last 30%, how much they are compared to the full size of Mars. But it's never been the intent of the human population to move to Mars. It's been the intent to be to get to Mars, to make sure that the human survive if there is an end of Earth kind of like event. If we get hit by a meteor and our life get destroyed, then it will be great if we have like 1 million people on another planet somewhere that can then make sure that the humans survive. We have had I think 5 extinction events on Earth already. And every time it's extinction, that means that nobody survives to tell the tale. So if we could get to another planet and keep a lock on what we are doing, we don't have to start over every time. So yes, from that point of view, Mars can definitely sustain the population. I personally, even though I'm talking about here, I'm definitely not the kind of character that want to go to Mars. I think that if we have a very big continent much further south, where in Antarctica, where it's cold and the weather is not always great, and half the year it's dark, like at least 3 or 4 months it's like dark. But there's still an atmosphere. You can still breathe. The temperature is like bitterly cold, but it's still like you can live there, and we understand that. And we still have very, very few people living through an Antarctic winter. So going to Mars, yeah, there's maybe not any snow, but it's not going to be much better what we find there. So I think there's going to be people who are adventurous enough that want to go there and live a place like this place. But it's not something where there's going to be 1 million people. I think is a big number. I'm just gonna go through the question.
There's another question. Yeah.
Yes. Would we find materials on Mars to build better technology? So that's certainly what we hope for. So right now, the last mission from the US, where I don't know if it was the last one, but one of the later missions they sent to Mars, they actually dig down in the ground to take samples, and those samples they then digged up and I put into a tube and I threw them on the surface of Mars, and I haven't figured out how to get them back yet. So right now we have a lot of samples, but they're still on Mars. So, you know, that doesn't really help. But the whole idea is to find out what Mars what Mars is like, and of course we have different ways of using. I think one of them has a gas chromatograph on it, so it can kind of like figure out what kind of elements it is, all that kind of stuff. But when the Chinese went to the moon here last time and they returned with a sample of the regolith from the moon, everybody was still interested in getting this to kind of like figure out what is it exactly. So independent of what kind of sophisticated technology we can send there to analyze it, it's much better if we can get in our hands. That what that mission to the moon definitely shows. And mining is one of them. So for example, on the moon, the reason why everybody want to go to moon is there's stuff there we already have identified that's very interesting. There's Judy, I'm getting into the chemistry here, so do me a favor, correct me, but there's something called heavy water, H3O or something like that.
Yeah, there's helium-3. So there's helium-3. So what it is that's helium that actually has an atomic mass of 3 and not 2. And that is extremely useful for energy production, running nuclear reactors. So yeah, we have very little helium-3 on Earth, but there's helium-3 on the moon. So that is a resource we have on the moon that we don't really have here.
So even though that's not a metal, I mean, it's still a gas, but it's one of the example of stuff that really, really want. And there's been other experiments of analyzing asteroids. So we've been sending missions to different asteroids and figuring out that they're like, full of different kind of metals that's interesting. So mining them and sending back. So mining in space, it's huge. And it's something that Judy is actually talking to the mining companies here in South Africa about, because we, of course, as part of BRICS, is also part of when China want to send something into space, they ask the BRIC fellows if they have some ideas. So mining is one of the big things that we want to do. Now, the reason I don't talk about mining is because living on any of these places is far different from mining. Mining on any of these planetary things we could do with robots. We should actually do that when we do mines here on Earth, and we can. So therefore, we should set robots to do that kind of stuff on different places, and they can then bring it back to Earth, which will be much more interesting. But in order to live on Mars, it will be also very interesting to figure out what is there. Right now, whatever we see around us here on Earth that we built, whether it's the Eiffel Tower or the Golden Gate Bridge or sky risers, different places, it's all built with stuff we found here on the ground. And Mars, of course, even though they lost the atmosphere, doesn't mean they lost a lot of the other material they have in the soil there. So if we can get it up, identify it, figure out how we can use it. Maybe there's nice lithium so we can build batteries there. Maybe there's the elements we need for doing cement or other binding material for the 3D printer, etc., etc. So we just have to kind of like figure that out. But that is going to be some of the first missions I can imagine when we start going to these planets, figure out exactly what is there and how can we use it.